uh, we will have to move 222 into the into positive offset. We will have a positive offset over here and a positive offset. uh, this will all become clear, more clear when we have a clear representation of stack, like how it is stored. So we will draw it later. An example continued. Push EBP. Yeah, all of this explanation is given over here. Start the function bar. Saves the incoming frame pointer. Incoming frame pointer. Let's draw a stack. Saves the incoming frame pointer. This is an incoming frame pointer. EBP. The value of this will be stored in this register. We will store it incoming frame pointer FP. Then we will set the frame pointer to the current top of stack, frame pointer to current top of stack. So we take the stack values and then we put it into we put it into the current frame pointer register. So we have a frame pointer over here. Most probably stack would be pointing over here. Then we take the frame pointer and we also point it over here. FP will point towards the stack. We subtract 16 minus SP. If we subtract SP as higher order addresses here, most probably here it is something like FFFF. If we subtract, then we go upward into the stack. We will go 16 bytes upward, which will take 4 4 2 3. It will point over here. 16 bytes upward, and then we will add a frame pointer is pointing over here, and now stack pointer is pointing over here. Move 555. Then we will decrease EBP. If frame pointer, this is negative offset. Negative offset means upward, and we will move 555 over here. 555. We will move. Then we will have a positive offset of base pointer, which is over here, and take EAX and take EAX from here. So most probably uh, these these arguments are uh, stored before this incoming frame pointer, because now the base pointer is over here. uh, b- uh, to a positive offset over here is the stored frame pointer, and now if we go one more step down and and another step down, we will take the value of the arguments passed to the function. We will take the arguments passed to the function and move to the register EAX, right? uh, EBP, which is this is an offset, which is second parameter. Okay, which is second parameter, and the third parameter would be like I said over here, and then it is incoming frame pointer, second parameter, first parameter, right? Second parameter and first parameter. We will take the second parameter in EAX, we will take the first parameter in EDX, we will add both of them and move into the EAX now, which will be uh, and we will uh, like this instruction shows that EAX is equals to EAX plus percentage EDX, and as the value of the addition is stored in EAX, we will move this EAX, have a negative frame pointer which will go upward, and we will store this value over here. It will represent X and this will represent Y. So here it will be stored A plus B. We will leave and return, right? In foo, uh, similarly, we will have a stack FFFF incoming frame. We will store the value of caller frame pointer, like caller frame pointers value should be stored over here. We will move the now here stack pointer will be pointing. We will move the frame pointer to the stack pointer. We will subtract the stack pointer by 8, as it supports only as it doesn't support uh, any of parameters. Go only 8, or else it would have went, like in this case it supports 2 parameters. it doesn't support any parameters, 0 parameters. uh, it moved over here, it moved 16, which is equivalent to 4 integers. Here it has moved uh, here it has moved 8, which is equivalent to 2 integers. You can see the difference, it is of 2, which which means it is our two parameters difference, right? So we will move it by 8. 8 means 1 2. We will move it over here, stack pointer points over here. We will move 2 2 2 into this positive offset, means downwards. Positive offset, we will have 2 2 2 stored over here. We will have 1 1 1 stored over here, right? And then we will uh, call bar call bar, and uh, it will then continue with this execution, right? So as we have understood this, we will move forward. Before the call to bar, uh, esp stack pointer, yeah, as uh, we have drawn over here that stack grows upward, here it is shown that stack grows downward. This is real, this is only for drawing purposes. Before the call, there is saved EBP 222111, as I've drawn over here. Saved EBP, saved uh, frame pointer. No, it was not shown over here. I guess I just missed this part. It should have been pointing over here. 222111 before the call. After this we have an okay. It was correct over here. It is return address is stored over here. Return address is stored. I was correct at this part, but uh, I just got confused. Return address is stored 111222. Saved EBP from foo. Like now we have gone into this. Saved EBP from foo. Then x, y, EBP minus 8, EBP plus. Now this is base pointer. Minus 4 means one step down, minus 8 means two steps down. Plus, here it would have been EBP plus 4, one step upward, plus 8 plus 12. Like this we can access and then perform operations. This is how call stack is being used while function calls. Like now we will learn about stack based allocation of space for subroutines. Subroutine A, B, B, C, D. Frame pointer will point at the lowest part, and stack pointer will point at the top of the stack. So yeah, it will first contain return address, as always, return address. Then it will have miscellaneous bookkeeping.
दिया हुआ है वो मेन प्रोग्राम पहले ए कॉल करता है, फिर तुम्हें बात है, फिर तुम्हें यहाँ से बी कॉल करता है, बी में तुम्हारा कंडीशन बी और सी कंडीशन, सी से फिर तुम डी और ई को कॉल करते हो।
ओके,
इस पर ये सब रूटीन कॉल, जैसे सबसे पहले मेन प्रोग्राम में ए है ना, तो तुम्हारा सब रूटीन ई कॉल हुआ, हम लोग खाली हुए, फिर जब तुम कॉल गए तो इससे तब तुम्हारा बी कॉल होता है, बी में तुम्हारा कंडीशन इफ़ या फिर एल्स, तो या तो बी खुद को कॉल करता है कभी कल, तो बी कॉल होता है सब रूटीन है, तो कभी सब रूटीन सी कॉल होता है। जब सब रूटीन जब सी कॉल होता है तो यहाँ से किसको कॉल करते हैं, सब
डी को, राइट। This was
यहाँ पर तुम्हारे
B has called itself once recursive before calling C. If D returns and C calls E, if D returns then C calls E. Okay, E's frame activation record. E's frame is will occupy the same space previously used for D's frame. We have got it. At any given time, the stack pointer points at the first unused location on the stack or the last used location of on some machine, and the frame pointer uh, register points at to the known location within the frame of current subroutine. The relative order of fields within stack frame may vary from machine to machine and compiler to compiler. Uh, yeah, okay, we all got this, but this is just representation of how a stack is allocated. Stack is used for function call. So first there is return address, then this is miscellaneous bookkeeping, I don't know why it is used, local variables, temporaries, and arguments to be called to the next routine, right? So subroutine nesting. In the language with nested subrouting and static scoping, in a language with nested subrouting and static scoping, Pascal Ada list scheme, static chain is used to locate objects. What is the static chain? We will understand later. Each stack frame contains a reference to a frame of lexically surrounding subroutines called static link. And what is dynamic link? Saved value of fp for return. The static and dynamic links may or may not be same, depending on whether the current routine was called by its lexically surrounding routine or by other routine nested in that surrounding routine. So what is subroutine nesting? In a language with nested subroutines and static scoping, like Pascal Ada list scheme, I don't know any of them, static chain is used to locate object. Okay, this what is the static chain? We will understand. Is it given over here? Static scoping for functions, nesting in subroutines, static scoping for function continued calling sequences. Calling sequences. So subroutine nesting. Static chain is used to locate objects. Each frame contains a reference to a frame of lexically surrounding subroutine. What does lexically surrounding subroutine mean? I don't know. What is dynamic link? Saved fp of frame pointer for return. Okay. Saved value of fp for return. I guess this is what is dynamic linking, most probably, I'm not sure. The static and dynamic links may or may not be same, depending on whether the current routine was called by its lexically surrounding routine or by some other routine nested in that surrounding. I don't know. We will move forward. If we understand it, we will come later. Nesting of subroutines with B, C, and D. All 5 routines are visible. A and E routines A, B, E are visible, but C and D are not visible. Given a calling sequence A, E, B, C, D, B, D, C, most probably it is A. Then it will call function B and it will call function E. This B will call function D. No, it will call function C at first, then it will call function D. But here the calling is done in opposite wise, and here it is given in different order. Okay. So first E will be called and then B will be called. Okay, this is A will call E, will call B. When this B is called, B will call D, then will call C. Okay, within B, C, and D, all 5 routines are visible. within B, C and D all 5 routines are visible. I don't know how 5 routines are visible, because if we call C, then all 4 of the routines will then all 5 of the routines will be visible in the stack. But if we call uh, within B and D, I'm not sure, because until C is called, C would not be there in the stack. Only this one portion will be there in the stack, and all 4 of them would have been present. So I don't know what uh, the writer has intended to understand over here. Within A and E, routines A, B, E are visible. Within A and how B is visible, I don't understand it. But C and D are not visible. Given the calling sequence AEBDC, in that order, frames will be allocated on the stack as shown at right, within with the indicated static and dynamic links. What is dynamic links? Dynamic links stores the address. Dynamic link stores the address of the calling function. Right. This is in the case of static linking, but in the case of dynamic linking, as we have understood, that saved value of FP for return. So this means A calls E, then E calls B. Most probably this is what dynamic linking is meant. Then B calls D, D calls E, C, and if we call it in this way, then we will get a stack frame like this, and the return address will return at D, right? So static scoping for functions, we will understand it over here, works similar for functions and variables. A is calling B, A is calling E, A is not calling C and D, E is not calling C and D, B is calling C and D, C calling D. What? Okay. In the case of static scoping, which I have drawn it over here and here, if resolution is not possible, we return unresolved error. F, C calling F, D calling F, A, B, E calling F, C calling B, C calling E. Static scoping for function call order. Static link will always point to the enclosing scope. Function call order. Static link will always point to the enclosing scope. Yes. Static scoping for functions. A, E, B, D, E. Indirect recursion. Nesting depths. Defined based on instruction or code return. Level pointer is incremented when we enter function and decremented when we exit a function. Static scoping for functions. If a function f calls another function g enclosed in itself, the static link of g is enclosed in itself and establish a frame pointer of f. A, B, C, E. The static link or frame pointer of E is established by the caller, that is C. Hence, a static link is dereferenced this many number of times: F C minus F E plus 1 times. We will see it again. Like static scoping for function, static scope works similar to the function for functions and variables. A is calling B. Okay, this is how functions are being function call order. Like we will come to this later when we understand more of it. What is calling sequence? Maintenance of stack is the responsibility of calling sequence. Okay. Like what will come in the stack? Maintenance of stack is the responsibility of calling sequence. Code executed by the caller immediately before and after a subroutine call. Code executed by caller Okay. This will be kept noted in the calling sequence. Like, what is a code uh, executed by caller immediately before and after a subroutine call? Like, when uh, A is there, what code has been called, then what code has been executed, B, and then what code will be executed later will be a responsibility of calling sequence. Subroutine, prologue, and epilogue. Most probably this will be prologue and this will be epilogue. Code performed at the beginning and the end of subroutine. Okay, subroutine is nothing but a function. Sometimes calling sequence include all three: prologue, function call, and epilogue. Fine by me. The calling sequence. The caller should establish parameters, establish the static link. The calling should establish the parameters, like it has to push the parameters, like what are to be passed to the function, callee function, which we have been calling, which will be calling. Establish a static link. What is the static link? Return address, as shown over here. What does the caller function do? It gives the parameter and makes the static link available, the return address available, right? The callee should update the stack pointer, right? We used to see that the stack pointer which points over here, after frame pointer points at the stack, it goes upward, right? Update the stack pointer. Establishment of return value, such as that the caller function can fetch the value. Okay, this is caller prologue, caller epilogue, caller prologue, caller epilogue. There is no clear line when there is no like, what is caller prologue and caller epilogue? Caller prologue and caller epilogue is just saving of parameters, saving of return address, and pushing it into stack. And what is caller epilogue? The fetching the fetching the what answer given by the callee, given by callee function, which is not written by programmer, not written by programmer, not written by programmer, which is already written when the function, when a C program, try.c, is converted into an assembly program, we get few extra steps, like saving the saving the returning address, pushing of arguments. Then this is caller prologue, which is performed in function f, and then the caller epilogue, which gets the value from the callee, or uh, pushing it from the stack, decrementing the stack pointer, right? Callee sequences. The caller saves the caller saved registers and those value which will be needed after the call, right? This will store uh, whatever whatever variable values it will have, it will store it at first, right? Computes the value of arguments and then moves them into the stack or registers, right? Compute the static linking if this is a language with nested subroutine, and passes it as an extra hidden argument. Okay, return address is also passed as argument. Hidden argument is also passed as hidden argument. Uses special subroutine call instruction to jump to subroutine simultaneously. A special subroutine named call instruction, which we have seen over here. It uses a call bar. This is a special instruction using special subroutine call instruction to jump to the subroutine, simultaneously passing the return address on the stack or in a register. We have got this prologue of callee, which is performed before callee is performed, performed before callee, allocates the frame by subtracting the appropriate constant from SP, allocates the frame, right? Here FP is there, stack pointer is also pointing over here, frame pointer, and then it moves upward by subtracting an appropriate constant from the SP, right? Saves the old frame pointer into the stack and assigns it an appropriate new value. Okay, the stack pointer, the frame pointer first points to the frame and then stack pointers goes over here. This is done before it. Saves the callee saves register that may be overwritten by the current routine. Callee saves register that may be overwritten by the current routine, including the static link, that is return address. Okay, static link and return address if they were passed in registers. Okay, I get it. Okay, calling sequence. After subroutine has completed, an epilogue is called. That epilogue does what? Moves the return value into a register or reversed location into the stack. Reverse location in a stack. Okay, uh, we obviously call a function uh, to get a value or to perform something, but if this function gives a value, then we store it into a register. This is done in an epilogue, which is done uh, after callee is performed. Restores callee save registers if needed, right? Stores the FP and SP, jumps back to the return address. Got it. Calling sequence. Finally, the caller moves the return value wherever it is needed. Restores caller save register it is needed. Okay, I get it. Over. Thank you.